This is lecture 4 for the General Motors 4L60E transmission, and with this lecture we're going to cover the hydraulic power flow, which means we're going to focus on the hydraulic schematics and explain what happens as we go through the gears. With each of these gears we're going to see the full hydraulic schematic before I start talking about it. Like for example, right now we've got the 4L60E while it's in the park position. You could tell it's in the park position because if you look at the manual valve, the way it's laid out here, the pin where the link goes through is lined up with the P position. So as we go through these different gears, you'll see it move. This pin will be lined up with reverse, neutral, drive, 3, 2, 1 as we shift to these different gears. And it kind of is weird the way it looks because line pressure looks like it comes in here and stops the manual valve. But it actually has the ability of getting in here and feeding some of these circuits. When you look at these hydraulic schematics, they color code stuff. And I did mention on a previous lecture that, like say for example, everything in red is line pressure. And even though it goes through the manual valve and it changes its name, as long as it's red, it's still the same pressure. So this now becomes PR, stands for park reverse. And some of these other pressures, like here we've got line pressure coming into our actuator feed limit. When it leaves that, it's modified and it's now AFL, actuator feed limit. The reason why we know it's modified because it doesn't share the same color anymore. It's not red. It's this kind of a brownish, goldish color, or whatever you want to call that. So same thing here, when the AFL goes through the pressure control solenoid, it goes in as AFL but comes out as torque signal. And since it's a different color, it's likely it's going to be a different pressure. At least it has the ability of having different pressures. So that's the way they color code these hydraulic schematics. It's nice. The way Hydromatic does this is really good. So when we go through these different gears, we'll take the opportunity to talk about what's unique or new. And for example, in this next slide, we'll talk about the only thing that's happening in park is the low reverse clutch assembly is applied. So when we shift into park, we've got the pressure regulator is going to adjust line pressure, and that line pressure is going to find its way in. The two different places it can go are both to the low reverse piston, and I kind of skipped around that. It can go through this low overrun valve, and it finds its way into this section, and basically these little white things on this piston are seals. So there's a couple surface areas that we have. We have a surface area here between those two seals, and then we have another surface area here between these two seals. And as you can see, they both have pressure in it. And it's because as soon as we shift this thing in the park, we open up this passageway that allows pressure to find its way between these seals here, the outer two seals, and then pressure going in this direction has its way of finding itself between the inner two seals. So this whole area, this full area has pressure. And if you remember, what they're doing is they're anticipating a shift into reverse. So they're going to go ahead and apply the low reverse clutch assembly. The low reverse clutch assembly holds that reaction carrier input internal gear, which is applied in reverse and manual low. So if we shift this thing into drive, it really doesn't make a difference because that low reverse clutch will release, but it is actually holding the same part that the low roller is holding. So it's not gonna, you're not gonna feel it either apply or release. So that's the reason why they leave that applied in park. So now when I go to shift out of park, I only have to apply one clutch, either the reverse clutch or the forward clutch. This is that low reverse piston. This is the outer seal, kind of the medium seal or middle seal, and this is the inner seal. And when we apply it in the low range, manual low range, we're going to apply this surface area right here. It's a smaller surface area. It's basically there just to prevent the low roller clutch from freewheeling or overrunning. And when we're in reverse, not only do we apply this inner section, but we also apply the outer section. We get the full, almost that full surface area. There's quite a few square inches actually of surface area that this works off of, so the amount of pressure that gets generated by this low reverse piston is pretty high. A couple things also you might have remembered on that hydraulic schematic is that pressure for reverse had this like check ball in line with it. And this was mentioned on an earlier PowerPoint, but these check ball, when it seats, it can pass fluid around either side of that check ball through these little notches cut out of that check ball seat. Then what this does is it allows for fluid going to this section right here, the large section of this low reverse piston assembly. It orifices that fluid, so it slows down the fluid as it enters that clutch circuit there, or that piston cavity. But when we take it out of reverse, we don't want this clutch to drag on, so it will allow the check ball to unseat and flow really quickly out. But that also means since we have two passages feeding this low reverse piston, we have the inner passage, between the inner seal and the middle seal, and we have the outer passage that feeds between the middle seal and the outer seal. I have two inlet passages for my valve body, for my case. So I need to air check both of those. I can fit an air nozzle into this one because it's just a hole, but on this side I need to use a plate or a rubber puck or something to go over it, because there's no good way of getting the nozzle to seal off against that check ball. But you definitely want to air check these things just to make sure that the seals are solid. You shouldn't hear any air leaks or anything when you apply air pressure into these. And once again, you always want to have the clutches applied, or clutches in the transmission. You don't want to put this piston in, put the retaining spring on there, and then immediately go air check it. Go ahead and build it up with the low reverse clutches and the low support and the snap ring and all that, then go ahead and check it. And when you're air checking this thing, not only will you hear it, but you'll see through this little cutout in the case, you'll see the piston going up and down. That's actually the wave plate and the clutches right there too. This is the complete hydraulic schematic for first gear. The only thing that really happens when we shift into drive, you can see the pin is over the drive passage there, is now line pressure has the ability of coming in and it enters this D4 clutch circuit. And in these following slides, we're going to review what's going on with the pressure switch assembly, but we're also going to look at the forward clutch accumulator. And this orifice 22 plays an important role, and this valve called the forward abuse valve, because all these things are in line with the clutch that we're going to apply, which is the forward clutch assembly in the input drum. And that's what really happens when we shift into and drive, and that gives us first gear, is only thing we have to apply is that forward clutch. So really what we talk about here hydraulically is how do we deliver fluid pressure to the forward piston, and how do we accumulate it or cushion it so that way we get a smooth shift. So we're going to focus on what's happening with the forward accumulator, the forward abuse valve, and the pressure switch assembly. So here's a kind of a quick review on the pressure switch assembly, because we covered it in lecture 3, the electrical and hydraulics presentation, but since it's part of the hydraulic operation, I figured I'd review it real quick. But when we shifted this transmission into D4, we've applied pressure now to our D4 switch. It was a normally open switch, and now since it has pressure there, it's closed. And that was also connected to range C. If you remember, I had A, B, and C ranges, or wires, circuits, coming from the PCM. And normally this would be 12 volts because it's an open circuit on the D4. And now that we've actually applied pressure and we've got pressure on our D4 circuit, that closes, and that range C finds its way through, actually goes through, range C goes through D4 and then through D2 to ground. So range C would be 0 volts as soon as I'm in drive. Range A is at 12 volts because it's looking at the reverse and the low switches to ground, and both of those are open, so we'd have 12 volts there. And range B is also at 0 volts because it finds its way from the D3 circuit, which is normally closed, and since there's no pressure it stays closed, and then to the D2 clutch circuit, and it's normally closed, so it's staying closed, so it has a path to ground. So anyway, our range A, B, and C, when we're in the D4 position, will actually be 12, 0, and 0. And that's just kind of a quick review of what we see as far as the pressure switch state's concerned. And we're using that pressure right from the manual valve to toggle that switch. When we also shift into drive, the D4 position, the only thing we have to accumulate, because the only clutch we have to apply, is going to be the forward clutch. And the way they regulate the shift for the forward clutch, and by the way, they call those garage shifts, because you're not really moving when you shift it into drive, at least you shouldn't be. So since it's a stationary application of a clutch, they call that a garage shift. And you can have a garage shift into reverse or a garage shift into drive. But so how do we accumulate this garage shift? Well, first and foremost, we have an orifice that all the fluid that's flowing in and applying that forward clutch has to travel through this orifice number 22. Its way up to that forward clutch. It also goes through and applies an accumulator piston. And if you look, this is a simple accumulator. It just has a spring. There's no back pressure or anything like that. So all we have to do is compress that spring. And it was like that. Actually, it didn't even have very early 700 R4s. Only had the orifice. It didn't even have a forward accumulator. And then what happened, let me just back up. The only reason why they did that is because they're like, well, it really shouldn't matter. If you just engine's idling, you put it into drive, if we just regulate through the orifice, we should be able to control the clutch application. And that is perfectly fine, and that's true. But the problem happens is that some people will be gassing it while they drop it into drive. And they'll be trying to deliver torque while this forward clutch is trying to apply. And what's going to end up happening is if you don't have any provision for that, you're going to end up smoking the clutch because this doesn't deliver, orifice 22 doesn't deliver the pressure quick enough. So how they combat that is they added this valve called the forward abuse valve. And they did all this actually back in 1986, 86 or 87, I think it was 86. So what happened now is when you shift it into drive, if you're on the gas and you're creating more line pressure, and it's like more than 100 psi, the fluid will actually push the forward abuse valve over to the right and allow it to enter this forward clutch feed circuit. And if you take a look here, it was able to bypass or go around. It didn't require that the fluid went through orifice 22. Fluid could go through orifice 22, but if you're creating higher pressure because you're giving it gas, giving it throttle, it can also go around orifice 22 because of the forward abuse valve. Now all the fluid, regardless, still has to flow into this forward accumulator circuit and stroke the accumulator. So it's still not good to do like what they call like a neutral drop, where you're in neutral, you're revving the engine up, you just drop it into drive. That's not healthy for the transmission at all. Yeah, we'd be able to bypass orifice 22 because of our forward abuse valve, but we still have to deal with stroking the accumulator and applying the clutch. So it's just a way of kind of adding a little bit of protection to this transmission because it needed it. So what accumulates or cushions our garage shift? We have our orifice 22, which we just got done talking about, that regulates how quickly the fluid can apply. We have our forward accumulator that gives fluid a place to go, so it allows for a more gradual rise in pressure once the clutch pack clearance is taken up. Then also within the forward clutch assembly itself, that bottom plate assembly is a wave plate, and even the piston return spring that's in there is going to operate as a kind of a dampening device, because as the piston travels, it compresses that spring. So those are the things that control the quality of the garage shift. If you have an issue where it slams in the gear or it slips in the gear, you probably have an issue. If it's slipping, you might have an issue with leaking or low pressure. But if it's slamming in the gear, it's possible one of these items are not doing their job here. This circle here identifies the orifice number 22. So all the fluid applying the forward clutch has to squeeze its way through that hole, which isn't that small of a hole, but realize that like this is the size of your typical bolt holes that you have. That's your general size. And all these smaller holes that we see, those are orifices that are there to regulate fluid flow. The check ball for the orifice 22 that was sitting next to it, it would seat off of this one right next to it. And so that allows for the forward clutch to quickly release when we shift it out of drive. It doesn't have to squeeze through orifice 22. It can just unseat that check ball and release real quick. This schematic here shows the 4L60E in second gear, and one of the things that we're going to focus on as far as second is concerned is the operation of the servo. We're going to look at the operation of this 1-2 accumulator assembly, and we're going to see how the shift solenoids are doing their jobs, because that's the first time we really are shuttling shift valves and redirecting fluid in that manner. So when we shift this transmission from first to second, the 1-2 solenoid goes from an on state to an off state. And if you remember from lecture 3, when they turn the solenoid off, what we end up doing is venting any of the fluid that's in there out. So that fluid was able to be trapped in there because the solenoid, there's nowhere for it to go. So the fluid that flowed through orifice 25, it built up on the back side of that orifice and caused this shift valve to stay shuttled over to the left. And now that we've turned the solenoid off, we're letting all the fluid on the other side of that orifice vent out. When we do that, we allow the spring on the 1-2 shift valve assembly to now shuttle that valve over to the right. And what happened is we took line pressure, which is this red pressure coming in from the top, which was being blocked by the valve. Now it's able to find its way into, and you can see they renamed it the second pressure. And that's going to find its way over and apply this, the clutch. You can see it also comes down, feeds through another orifice, and goes through the 2-3 shift valve. And we'll see, it's very important to realize this because you're going to find out with these later gears that all the other gears, second, third, and fourth gear, actually originate from the second pressure. So we require the 1-2 shift valve to shuttle and allow this second fluid circuit to fill up to allow any of the other gears to operate. So to make sure I cover all this stuff here, when the PCM commands second gear, it opens the ground circuit for shift solenoid A, which is the 1-2 solenoid. Spring pressure then pushes over to the right, and that's the upshifted position. And the second fluid is going to apply the servo, which we'll see coming up next. So that second pressure, when it came in, it got diverted over to the accumulator, which we'll talk about in a minute. But it also comes down, finds its way right into this passage that fills this section of the servo assembly. The servo is kind of an interesting component. It applies in second, gets pushed back in third, and then reapplies in fourth. Right now what we're looking at is the pressure that's there in second. You can see the surface area of the apply area for second is right through here. I'm coloring it in the blue on the servo. So I've got the surface area that exists basically from this inner seal to the outer seal, and all the pressure that I generate in there is going to be working on that surface area to move the servo pin and apply the band. We actually have 3 different servo assemblies. There's actually 4 different, but I only have pictures of 3. And I don't remember the number of the 4th. It has a different number, and it lives in between these 2. This was termed a high performance or Corvette servo. It actually has the 092 stamp, the last 3 digits of the part number, say 092 or 092 on it. And it has the greatest surface area. So the surface area is going to be from this, basically this divider piston that I see right here. That is equivalent to the surface area that the piston has, because the fluid is going to go between the outer seal and the inner seal. And you look, that's pretty much that dimension right there. The medium size is the 553. The last 4 digits or 3 digits are 553. And you can see those part numbers. You can't really read them, but they're on the servo itself. And it's a little larger. The center area is larger. The outside diameters are obviously going to be the same on all 3 of them, all 4 of them. But what happens is this inner surface area right here, of the circle here, that gets larger and larger. And when it gets larger and larger, it creates less surface area. You look at the 554, it even has less yet. So I don't have as much surface area on the 554 as I do on the 553, and the 553 doesn't have as much surface area as the 092. And like I said, there is one more that fits in between the two here. I don't remember what the code is. And that for forever, it seems like they had these three, and then GM made a fourth. And like I said, I just don't have those. But the surface area you can see drawn on this schematic here on the left. And so when fluid pressure comes in there, it's going to exert its force and apply that servo and apply the band. Some people will go through and take out whatever servo they've got and make sure they've got the high performance one. The aftermarket makes even more aggressive servos. So, and it is a balance actually. I don't want to say that just take one out and put a different one in, because as we're going to see when we shift into third, we don't get rid of the second fluid pressure that exists here. We don't get rid of it. What we do is we add to it, or we use fluid pressure on this side, on the back side of it, to push it off. So by increasing the surface area in second, I'm actually making it a little harder to remove that band in third. So something to be aware of. And next we'll talk about how this accumulator works, even though we did cover that on lecture 3, but this will be a review. Basically how this is all regulated is when we shifted this transmission in the second, the fluid from the 1-2 shift valve entered the second fluid circuit, and you could see we're automatically going to be regulating how quickly the fluid can apply in there by orifice number 16. That check valve number 8 seats, and orifice number 16 is going to now regulate all the fluid that enters into that circuit. And that fluid that's entering in that circuit afterward is going to be directed over to the accumulator. You can see I've got springs on the line pressure side, and then I've got accumulator pressure on the other side of the accumulator piston. Now I'll tell you this, what confuses people a lot when they're looking at this. This almost looks like the 3-4 accumulator side and the 1-2 accumulator side are sharing the same fluid cavity. And they're not. There is the spacer plate that separates the valve body from the case is actually right between there. Now, yeah, there are green fluid and it's the same pressure, but they are separate. These two circuits are separate from each other by gaskets and a spacer plate that divides it right down the middle. It just doesn't do a very good job of showing that. So when we shifted in the second, and that second pressure came in, its job is, once it overcomes whatever the accumulator pressure is, it squeezes the accumulator pressure out, comes around, the pressure increases on the end of this valve because the line pressure is actually forcing the accumulator pressure to go up. And when that accumulator pressure goes up, it moves the valve over to the left, and when it moves the valve over to the left, it's going to open up this exhaust passage and it's going to leak all the excess accumulator pressure out. And that's the job of the accumulator. If you remember, the idea of the accumulator was the accumulator fluid was to create a variable back pressure on this accumulator piston. So when fluid pressure came in here, not only does it have to, in most cases it would compress the spring, but in this case it doesn't. But in addition to just stroking this piston, it'd have to squeeze the fluid out. Well, you know, if you're a brakes guy, you'd be like, well, you can't compress fluid. There's no way. There's a law, hydraulics law, that says fluids cannot be compressed. Well, that's true, but when I have a higher pressure on this side, let's say 150, and if I have a lower pressure on the other side, let's say 70, that 150 psi is going across the same surface area is going to try to raise this pressure to 70 psi side. It's going to try to raise it to 150. Well, this accumulator valve is not going to like that. It's not going to, once it sees 150 psi, this valve is going to move over and it's going to allow the pressure to exhaust out. So we won't actually see the pressure go any higher than what the accumulator valve wants it to, because the accumulator valve will just open up and exhaust the higher pressure out. So that's how they regulate it. And you can imagine if I'm at light throttle or heavy throttle, since the torque signal has the ability of changing the accumulator pressure, I can change the amount of accumulator pressure on the other side of the piston, or the accumulator piston, and then I get a varying effect on my 1-2 accumulator to kind of handle the different loads and output of my engine. That is orifice number 16. So all the fluid that goes into the second clutch servo circuit has to squeeze through that orifice. As I mentioned before, the accumulator pressure is generated by this accumulator valve. Line pressure comes in and finds its way into the accumulator circuit. Once there's enough pressure in there, the accumulator valve will move over and cut off its own feed there. Won't let any more in. If I want more pressure, my pressure control solenoid will increase torque signal pressure, and it will push this valve over to the right, and that would allow more line pressure into the accumulator circuit until I got enough to basically regulate itself, move itself back over, and cut itself off again. So it's a balance valve, just like a lot of these regulator valves that we have, except the difference between this one is it can change. It's not just a fixed regulator valve. It has the ability of changing pressure by adding the torque signal pressure on the side of that accumulator valve. Just another example here, at wide open throttle, high torque signal pressure, which should be about 115 psi, will add with the spring and force this valve over to the right as far as it can, and this allows a lot of line pressure to enter the accumulator circuit. Once enough enters in that it can overcome that 115 psi and that spring, it'll move the valve back over to the left and cut off its supply. So as I change my torque signal, I actually change the amount of pressure in my accumulator circuits. If you also remember from the previous lecture, lecture 3, that they do offer different valves with different sizes on the end here, and then of course like 5 or 6 different springs that change the amount of fixed tension. This is the complete schematic for third gear, and we're going to look at how the shift solenoids change to give us third gear. Realize that when we shift into third, our 3/4 clutch applies and our servo releases, and it uses the same pressure to do both of those. So the timing's pretty critical. So we'll actually look at some of the issues, like they've got this accumulator check ball right there that has a potential of leaking, and we'll look at the accumulator, or the accumulation really is done by the servo when fluid pressures enters that circuit. So we'll focus on those topics there. When we shift into third, we have this 3/4 clutch that applies. That's a notorious clutch there. It is notorious because it fails frequently. I'd probably say 8, I don't know if that many, but maybe a 6 or 7 out of 10 4L60Es that come in for repair probably had a 3/4 clutch problem. A lot of them will also break a sun shell. That's really common, especially the older ones. And then some of them will run into sprag issues. But those are the 3 areas that are probably their weak links. And there's a lot of aftermarket considerations you could take for those. But yeah, the 3/4 clutch, when it applies, at the same time it's applying, we're releasing the servo by applying third pressure at the servo assembly. This is the only shift in this transmission that is synchronized. When I say synchronized, I mean you are actually timing the apply and the release of a clutch. Because when we shifted from first to second, all we have to do is apply a band, and then the low roller freewheels. So we don't have to synchronize the release and apply of a clutch. Here we're talking about the 2/3 shift, and they have to sync the release of the band and synchronize the apply of the 3/4 clutch. And when we shift into fourth, as you'll see, all they have to do is apply the band again. They don't have to release anything. There are some transmissions that are out there, and really no new ones anymore because there's just too many speeds to make this happen. But there are some transmissions that are out there that they don't have any synchronized shifts, like a 4L80 for example. When you shift from first to second, they apply an intermediate clutch and then the low roller freewheels. When you shift from second to third, you apply a direct clutch and then the intermediate sprag freewheels. And when you shift from third to fourth, an overdrive clutch applies, and there's an overdrive sprag that freewheels. So all they have to do, they never have to release the clutch when they're upshifting, and they only have to apply one. So that can make for a really smooth shifting transmission. This is, for the most part, one of those transmissions, except for the 3/2 upshift or the 3/2 downshift or the 2/3 upshift. you have to synchronize those. And we'll look at how they do that here on some of these slides. The shift solenoid B, or the 2-3 solenoid as it's also called, it turned off. A was off from the 1-2 shift, and it shuttled over to the right and allowed us to fill the circuit with second fluid pressure. And now when we shift into third, we turn B off. So you can see there's no pressure on the other side of orifice 29 there. And allowed this valve to shuttle over to the right. And it took our second fluid pressure through orifice 28 and now goes into the 3/4 signal pressure circuit. And that's going to operate and apply our, release our servo and apply our 3/4 clutch. This is the orifice for that. So that orifice number 28, that's just right next to the 2-3 shift valve. So everything that goes through and turns into the 3/4 signal pressure, everything has to squeeze through that hole. And it's not that small of a hole, but the reason why I'm making a point out of this is because there are going to be some natural leaks that we have in the transmission. There's going to be some that are engineered in. For example, when you go through an air test, if you remember when you air test that 3/4 clutch, there's an air bleed in there. You have to put your finger over it because you'll always hear it leak if you don't put your finger over it. So there's an automatic engineered leak that is in that 3/4 clutch circuit. Also, in the servo assembly, there's an air bleed in it. So when you're releasing the band by applying the third fluid pressure on the case side of the servo assembly, they have an air bleed in there that is really there to get air out, but a lot of people believe it's there to lubricate the band because the air bleed's squirting directly towards the band, and there's actually a hole cut in the band that allows it. So I guess it's not really lubricating the band, but lubricating the reverse drum. But still, once again, there's a hole there, and it's engineered. So now I've got two engineered bleed orifices that are always passing fluid. And if I created some other leaks, that maybe through Teflon seals, maybe through a slightly cut piston seal, or a bad connection on the spline or something, every time I create another leak, if I ever get to the point where I come close to the size of that orifice, by the time you add up all these leaks, then I can't maintain pressure on the other side of this orifice, and I could run into a clutch that slips and burns up. That's the reason why this 3/4 clutch is also kind of the weak link in this transmission. So if you run into 3/4 clutch failures, you want to make sure that there are no leaks anywhere in this transmission on that 3/4 clutch circuit. The 3/4 clutch needs to apply when the 2/4 band releases, and they have to be timed. So when you think about what's happening on an upshift, when you're driving, your engine's revving up, and then when you upshift, your engine comes down. Let's say, I don't know, a normal shift, it might come down 400 or 500 RPM. That means that 3/4 clutch actually has to come on while the band is still applied. And then that's going to bind up the transmission a little bit and cause the engine RPM to drop. But before it drops too much, that band should release, and then boom, you're in third gear. If the band releases first, and that before the 3/4 clutch had a chance to apply, you're going to get a flare. The engine RPM is going to rev up and then come back down. If the band stays on too long when the 3/4 clutch is applying, and both of them are on for too long, it's going to bind up, and then when it finally does release, it will let go, and you'll feel, it might feel like it's throwing you forward every time that you shift from second to third. So it's a balance point, and that's the reason why we see some of these circuits in here. We got orifices and accumulators and springs, and there's different ways to kind of manage the shift, especially on the downshift, that they're trying to smooth that out or handle any of the circumstances that surround the 2-3 upshift or the 3-2 downshift. So fluid, the signal fluid, when it comes in, it's going to go through, it has to go past, doesn't have to go through the orifices, but actually will go past it. So these orifices 13 and 12, those aren't actually there for the apply of the clutch, they're there for the release. and then that fluid comes up. It's actually going to seat this check ball. This check ball, by gravity, is normally going to be hanging out down here, but when fluid pressure enters the circuit, it slams that check ball up against its seat and allows the fluid to enter the servo assembly. And you can see here's my second fluid pressure. It's still there. They don't exhaust it. When we shifted from first to second, we created the second pressure, and we shift from second to third, we still have second pressure. Matter of fact, second pressure is the source of the fluid pressure that we're using to apply the 3/4 clutch and release the servo. So this fluid coming in here is going to work across a larger surface area, and that's the reason why we're able to use this pressure to overcome the second pressure and push it back. So I'm looking at a surface area on one side, on the third side, between the case and the servo, that's basically utilizing this whole area right here, and that's going to be greater than the surface area that the second piston is working off of. And since I can overcome it, so long as I don't have any leaks or anything like that, I can push the servo back, and that releases the band. This spring that lives inside here actually works as an accumulator. The spring and the pressure coming in here will kind of compress that spring. It moves a little bit, this plate assembly that's in there, and that's what dampens or cushions the shift. So there's no separate accumulator per se that we see, kind of like we have over here's in the back of this drawing back here, but you can see those accumulators. Even the forward accumulator is on the schematic somewhere. But there's no separate standalone spring and piston. They're utilizing this side of the servo as the accumulator for third. There's that air blade I was telling you about in the previous slide, where the fluid squirts out of that air bleed and actually squirts on the band. And there's a hole in the band so the fluid can get through and get on that reverse drum. I don't think that's really the purpose for it. I think there's plenty of fluid going around that they probably don't have to worry about that, but they need to get the air out, so to make it a consistent shift. And that's my guess, the reason why they do it, but it just works out that it'll also lubricate that band. So yeah, that's also, if you mentioned from the previous, or remember from my previous slide, that changing that second servo piston, where we have a different size piston that's working in this area, like a Corvette servo, the 092, that affects how this third fluid releases that servo. When you switch out the pistons, some of them will go through and want to drill out that kind of increase the size of that orifice. I believe it was orifice number 28, that was just before the 2-3 shift valve. That allows the fluid to come in here a little quicker, because we have to overcome more when we have a larger, like a high performance piston in there. I mentioned here that some problems occur with the 4L60Es when check ball number 7 does not seat properly, or it leaks. If you remember back when I was talking about that orifice, and I had that hole, and I don't have it shown up here on the screen, but that orifice is only so big, and I've got engineered leaks, like that one in the servo. There's an engineered leak up here on the, I don't think it's drawn, but it's up here on the 3/4 clutch, the input drum. And heck, you can leak a little bit around the servo pin where it goes through the case. There's potential for leakage in a bunch of different places. So if the leaks, a little leak here, a little leak there, a little leak here, all these little things, if they start adding up and they come close to the size of the actual orifice, then now you're in trouble, because you're not going to be able to maintain pressure on the other side of the orifice if all the leaks on the other side of the orifice end up being bigger than the hole itself. And this number 7 check ball is kind of an area that gets pointed out, where if you end up having leaks through here, you're going to drop the pressure in your 3/4 circuit so much that you're going to end up burning the band, because it's not going to release the servo like it should, and burning your 3/4 clutch, because it's not going to be able to release or apply the 3/4 clutch like it should. So if you take a transmission apart and you've got a burnt band, the reverse drum's all burnt up, the 3/4 clutch is bad, definitely, in addition to many things, check your accumulator number 7 there, make sure it seals, it's in good shape. A lot of issues also arise the input shaft that fits into the input drum, the splines can leak out. So when you're air checking this, because the 3/4 piston is this one on the very back, so there's not much meat, there's not much aluminum. If you take a look, and this is, I know I'm going through a shaded out picture here, but the amount of aluminum that exists between the splines and that 3/4 shaft and the 3/4 cavity, they're small. And that fluid can kind of squirt right out through there. And it's not going to come out much, but if you put solvent in there when this drum is warm, hot, you're supposed to heat the drum up because the aluminum will expand. If you put a little bit of solvent on top of it and then you air check it, if you see bubbles coming out around that thing, that's not a good sign. It's going to leak. And if it leaks, you're going to burn up that clutch. So what do is a lot of people press that shaft out, put Loctite or sleeve retaining Loctite on there, press it back in, and that usually helps it live. Here's the complete schematic for the 4th gear, and we'll look at what's happening in the 3/4 accumulator, what changed in our accumulator, or our servo assembly, and we'll see how our shift solenoids changed, because our 1/2 shift solenoid now turned on. That actually kind of shuttled our 3/4 shift valve, and we'll talk about that a little bit. Looking at our shift solenoids, what changed is the 1/2 shift solenoid turned on. And to look at this, you might be asking yourself, well, if that turned on and it's now built up this signal A pressure here, how come this shift valve didn't shuttle back over to the left as shown, like it was in 1st gear when the solenoid was on? And the reason why is when we shifted from 2nd to 3rd and we turned the 2/3 solenoid off and this 2/3 shift valve shuttled over to the right, AFL pressure was able to find its way through this 2/3 shuttle valve, and it found its way to the end of the spring side of the 1/2 shift valve, and it added to the spring pressure. And the blue pressure that we have with signal A, that's AFL, just renamed and recolored. And then if I put AFL on the other side of the shift valve with the addition of the spring, that shift valve will stay positioned over to the right and it won't downshift. Now, we don't want it to downshift, not when we are asking for a shift from 3rd to 4th. When we go back down through the gears and we shift back into 1st, this AFL pressure that exists on the spring side, it won't be there anymore, so we'll actually be able to fully downshift that valve. But right now what we're doing is we're using shift solenoid A, or the 1/2 shift solenoid, and we want it to not only do its job shifting from 1st to 2nd, but also kind of serve a double duty there and shift this 3/4 shift valve as well. So when we energize the circuit and we trap the fluid pressure in there and AFL builds up and it's called signal A now, we look and we come over, we shuttled the 3/4 shift valve over and it's shuttled over to the left as shown there. And what happened when we did that is we were able to take this 3/4 signal pressure, and where it comes up, it's now going to be able to go through the 3/4 shift valve. We'll see where it goes next. But also realize that, I mentioned this on slides before, everything still is originating from the 2nd pressure. So if this shift valve never upshifted, we would never get 2nd, 3rd, or 4th gear. So that's kind of an important thing to have, is make sure that this shift valve is doing its job. To continue tracing this shift valve circuit here, the signal pressure then turned into 4th signal. And that 4th signal pressure goes over to this 3/4 relay. And from the 3/4 relay, we have this fluid pressure coming in. And find it, I lost it. Okay. Okay, it's coming in from here, the 2nd fluid pressure. 2nd fluid pressure finds its way into what we call the servo feed. I'm going to change colors. We have to squeeze it through orifice number 7. And then we find our way into the 4th clutch circuit, and then we follow this around. We'll see it goes through the servo pin, right through the middle of the pin, and it comes out at the end of the pin and works on the 4th piston. The 4th piston is the piston on the end of the servo assembly. So in 2nd, we were working on the 2nd piston of the servo, and that applied the band. In 3rd, we had fluid pressure work on the other side of that second servo piston, and that pushed it released. Well, since I don't exhaust second or third pressure, there's the second pressure and there's the third pressure. Since we don't exhaust that, fourth pressure came in on its own little path, found its way through the pin, and worked on this fourth piston, which is completely separate from the other components, and was able to move the pin. Not the whole, this assembly still stayed shifted away from the case. Now we're moving just the piston, the fourth piston, and the pin, and applying it. It's kind of a neat little servo assembly that they've got. While we're doing that, we're having to accumulate it. And obviously we saw the way they accumulated it. They're using this orifice number 7 as one method. But we also have the fluid coming in from this accumulator circuit, the 3/4 accumulator. And as fluid pressure finds its way into the accumulator circuit, it's going to compress the 3/4 accumulator spring, and it's going to squeeze that fluid out. It's going to squeeze it on out right through the accumulator valve as it's stroking the accumulator piston, just like it did on the 1-2 accumulator. This is that orifice number 7. It's not that small of a hole, so it's not, but like everything else, leaks can add up and can cause problems. If anything ever gets on the other side of that orifice, if any leaks get bigger than that hole, you're gonna slip. You're not gonna be able to generate any pressure, and you'll just have a band that slips. This is kind of like a review because we've talked about how this accumulator works. It's not much different than the 1-2 accumulator, other than the fact, now remember, there is that plate that divides these two. Otherwise, you'd be looking at that wondering how the spring is just kind of floating there. But the spring is about the only thing that makes this 1-2 accumulator and this 3/4 accumulator different. On the 1-2 accumulator, the spring helps line pressure push the piston. On the 3/4 accumulator, the spring works against line pressure and helps accumulator fluid pressure. So whatever accumulator fluid pressure I have in here, let's use that example earlier. If I had 70 psi of accumulator fluid pressure in there and I got 150 psi of line pressure coming in, the 150 psi is going to it's going to try to raise the 70 psi side up to 150, but it won't be allowed to do that, because when you're raising that pressure that's going to come around, work on the end of the accumulator valve, the reaction area of the accumulator valve, move that accumulator valve over to the left, and that'll end up opening this exhaust passage and allow the fluid out, that exhaust. So that's how the fluid gets out. We're using line pressure on one side of the piston to push the accumulator fluid pressure out through the accumulator valve. Now we're going to look at the torque converter clutch application. In the early 4L60Es, I actually ran into quite a few problems with the torque converter application, mainly because of this component right here, this regulated apply valve. It ended up wearing out, and then the fluid that's supposed to apply the torque converter clutch, it ended up just leaking out and not building pressure in the torque converter apply circuit. So we're going to look at what's happening to the enable solenoid. They call this the enable solenoid, or the on-off solenoid. And we're going to look at what's going on with the PWM solenoid. The PWM solenoid is what creates the pressure to apply the torque converter clutch, and the variable, because they'll actually let these torque converter clutches slip at low speeds, and so that way they can bring them on earlier. And then after you get to a certain speed and the conditions are right, then they'll lock them up fully. But when you're in lockup mode, it looks at engine speed and output shaft speed, and it can kind of calculate what the torque converter clutch slippage is. Assuming that none of the clutches are slipping in the transmission, they can use the gear ratio of whatever gear they're in, plus look at engine speed and output shaft speed, and they can figure out how much the torque converter clutch is slipping. So we have two solenoids. The torque converter clutch enable solenoid, it's the one that's responsible for reversing the fluid flow through the torque converter. And this solenoid right here, it's the one that's bolted to the case, and the snout of it goes through the oil pump. It's the one that you want to make sure you remove before you try to take the oil pump out, or else you'll snap it. And I know that because I've done it a bunch of times. But how does this thing work? Well, line pressure, that's right now this is showing it in the apply mode. So should really show you one in the release mode first. But in the apply mode, fluid from the pressure regulator is actually just being directed to the oil cooler and through the lube circuits. And fluid from the regulated apply valve is going to find its way through the converter valve and into the apply passage. The apply passage is going to be between the converter hub and the stator support shaft. So if I'm entering fluid in on the turbine side of the converter piston, I'll drift that piston over and actually cause the piston to make contact with the cover, like it is right there, and it'll apply the converter piston. When I'm in the release mode, fluid will go through the center of the input shaft and it'll push the piston away as it feeds the converter with fluid. The PWM solenoid, or what it's also called in scan tools, the control solenoid, as you would think with the term control solenoid, it's responsible for controlling how much pressure is on the torque converter clutch piston, and it can regulate it. Since it's pulse width modulated, it can change the pressure as needed. And what they're doing is they're taking AFL pressure, and as they pulse the solenoid on, they're creating what they call a CC signal, or converter clutch signal pressure. That pushes on this valve they're calling an isolator, and through a spring it's going to push on this regulated apply valve. When that moves that valve over to the left, it's going to let line pressure into the circuit, and they call that line pressure regulated apply pressure. And that ends up being the pressure that finds its way into the converter to apply the piston. If they want more apply pressure, they'll just continue to turn the solenoid on at a higher duty cycle, because then they'll let more AFL and more AFL. So this really, they can put between 0 and 115 psi on this reaction area of the isolator valve. And that's going to change, because all these valves are the same size, so that's basically going to change the apply pressure between 0 and 115 psi. And that's quite a bit of pressure. That's more than enough to apply the torque converter clutch. When you think these converters are 10-inch converters, and you're really working across the whole surface area for the most part. So that's about, well, radius squared, 5 times 5 is 25, times pi, let's say 3, so you got 75 square inches. Even if you were operating at 100 psi, that would be 7,500 pounds of force. So that means this piston is strong enough to lift 7,500 pounds of force. And my Chevy Tahoe only weighs 5,000 pounds. So when this torque converter clutch is applied with full pressure, that's enough to lift 1.5 times my Tahoe off the ground. And that's, you know, that just puts that in perspective of how much force we've got with these hydraulics that we have in this in these transmissions and this torque converter in general. So that's what we're going to be doing. We're going to be pulse width modulating our torque converter clutch solenoid to get this converter piston to apply with enough force that we're not slipping this clutch. And they'll look at the engine speed and the output shaft speed to see if that torque converter, and then on the later 4L60s they actually have an input shaft speed sensor, and they can look at the engine speed and input shaft speed, and then they can finally control the PWM solenoid to get it so that way they're not seeing any slip. And once it doesn't have any slip, they don't necessarily need to apply any more pressure than that, and they'll just operate the transmission that way. So let's make sure I covered all this information. We use AFL pressure to modify this regulated apply valve by creating this CC pressure. Regulated apply valve modulates line into torque converter clutch apply pressure. This valve wears out and causes all the TCC apply pressure to drain before reaching the converter. So this valve, when it wears out right here, and you'll see this in the rebuilding particulars PowerPoint, When it wears out, the fluid could sneak out through this exhaust. And when it sneaks out through the exhaust, the fluid pressure that it's letting in never found its way into the circuit to apply the converter clutch. It just leaked out. So instead of having that 100 psi or whatever it may be in there, it might have 10 psi, and that's just not enough to apply a converter piston, and you'll slip it, causing the converter overheat, turn blue. You'll create a code, an 1870. On the later model ones, it's like I'm going off of memory, but I think it's a 742, and you might overheat your transmission. So bad news all around. There are a lot of fixes for this out there. There's valves that you can put a Sonex valve in there. You bore it out and you replace that valve, and you replace the aluminum in the transmission, the valve body, with a higher quality aluminum that doesn't wear out as well. Transgo makes a drop-in valve that's got some fixes. Superior. There's a few different companies that have ways of fixing this. Even General Motors, when they rebuild it, you get a remand from them. They bore out the case and put a bigger valve in there. But the problem is that the casting is what's soft and wears out. So just boring out the existing valve body and putting a bigger valve in there, you're still going to wear that one out. So really the best option is to use like the Sonex valve, where you bore it out and you end up putting in a new bushing in place of the metal that you bored out, and then a valve in there, so that the new valve is working on this fresh aluminum that's a higher grade and doesn't wear out as quickly. When we want the torque converter clutch to apply, the process that occurs is we turn the enable solenoid on. That shuttles the torque converter clutch valve up, and allows now fluid from the regulated apply circuit to feed the converter. And then we start pulse width modulating our solenoid. Usually they have this thing, when this torque converter clutch solenoid is off, this is sitting at like 95%. We'll see it just sitting there, and the reason why is they'll have this whole circuit primed with pressure, ready to go. And then as soon as they want this torque converter clutch to apply, just before they turn the enable solenoid on, you'll see the PWM drop from like 95%, it'll go all the way down to like 10% or so. And then once the enable solenoid's on, they'll ramp it up to about 30%. And this is going to be different for every vehicle, because it's an adaptation that they learn. What do they need? How far do they need to apply this PWM solenoid to get it so it won't slip? The torque converter clutch won't slip. And then when you get to a certain speed, it usually bumps it up to like about 65%. That's a pretty common process, and you'll see that every time the torque converter clutch applies. By doing it this way, they can make that converter clutch apply so softly that you don't feel it apply, but also they don't pump pressure into this converter during the apply mode. They don't pump more pressure than they need. So I mentioned this earlier, but the PWM solenoid is normally closed, so if you have it turned off, you don't have any pressure. And then when you turn it completely on, you get 115 psi, because it'll let AFL go straight through into it. And it creates that converter clutch signal pressure here. And if you look at the valves, these valves all have the same lands. So if I got 115 psi pushing this valve over to the right, I'm going to need 116 psi of line pressure in there to move it back over. I said that backwards. If I have 115 psi of pressure in this converter clutch signal pressure moving this valve to the left, I'll need I'll need just a little bit more pressure working on this reaction area here on the side of this valve to overcome it, to move it over, to cut itself off there and not allow more in. All those valves are the same size, so it's just a balance of pressure on each side. These are just kind of a few states. If I have 100% PWM, which it really doesn't do 100%, but let's say if I have 100% PWM, I'm going to have full CC or maximum CC pressure. That's going to end up being maximum regulated apply pressure. And I'll have a full torque converter clutch application. If I have 40% as an example, I'm going to have something less than maximum. Let's just say, because I kind of guess at this, since 0 is 0 and 100% is 115 psi, I'm going to say that we're probably going to be around, I'm going to say 50 psi. So I have about 50 psi of converter clutch signal pressure, which also means I have about 50 psi of TCC apply pressure. Oh, drew that on the wrong line there, but that means I'm going to have about 50 psi inside my converter applying that clutch. If that's enough to apply the clutch and create no slippage, then they could stop there. If I have 10% PWM, I'll only have about 15 psi in this converter clutch signal, which means I'll have about 15 psi of regulated apply, and only 15 psi of torque converter clutch apply pressure, so I probably won't have enough pressure to apply a torque converter clutch, but I'll start bringing it on and it'll start bridging that gap, so and the speed difference, and that's the starting point. So I bring it on at 15%, it engages, and then I can slowly start ramping it up and make it apply real smoothly, and that's what the computer does. The PCM is going to vary that pulse width modulation to improve drivability. This chart here looks crazy. There's a lot going on. This is actually a snapshot from Tech 2, but I've got on here in red the throttle position sensor, so you can see what I'm doing when I'm driving it. Looked like I was wide open throttle here, and then I took my foot off the throttle. This is probably a deceleration through here, and then slight acceleration through this range here, slight acceleration. In this light green, lime green, whatever you want to call it, that's the torque converter clutch enable. This would be off and this would be on right there. In blue, we've got the torque converter clutch slip speed. You can see the slip speed's kind of going up high, then it drops down low, and then it kind of floats around, with the bottom of the graph being -100 and the top of the graph being 1500, to kind of give you an idea of the range that we're looking at. And this teal color is our pulse width modulation of our torque converter clutch solenoid. You can see it kind of floating around there. It even jumps up pretty high at some point. This is when the torque converter clutch is released. It's sitting there at 95%, just waiting until it's ready for the apply mode. Then we got our vehicle speed, kilometers per hour. That's pretty close to 60 miles an hour. And the engine speed in gold. See what my engine was doing. So at this point you could see the torque. If you look at where the arrow is down here, the numbers that you see up there, this values up here are going to be representative right above this arrow. So if you look what's going on here, and this is examples, up here the torque converter clutch enable is off, and the PWM solenoid is, so when we see the enable solenoid is off, that's just before it went from off to on, we could see the enable solenoid was floating while the enable or I'm saying this backwards. Let me restart that part. If the PWM solenoid is sitting high when the enable solenoid is off. There we go. Now I'm saying that right. And then you can also see just before they command the enable solenoid to turn on, they take the PWM solenoid and drop it way low. So they know they're going to turn it on, so they go ahead and give it a little bit of time to drop the PWM solenoid down low. So dropped it down to about 10% probably. And once it was down to 10%, they went ahead and turned the enable solenoid on. And once the enable solenoid's on, the torque converter clutch is starting to apply, they start ramping up gradually the PWM solenoid, and they monitor the slip speed and see if the slip speed is starting to drop. At this point right here, where that arrow is, the values, we saw a 24 RPM slip speed, 38% duty cycle, and our torque converter clutch was on. Now we're going a little or not much faster, but we're up to speed. Here's my arrow, so the values that you end up seeing on this graph are going to be representative of that section of the graph that we're seeing. You can see I'm slowly going a little bit faster, and you can see I'm on the throttle. I actually kind of increased my throttle pretty high at this point. I was at, doesn't have percentage, but 1.78 volts, so I was probably at about 20% throttle or maybe a little more. But you can also see with the PWM solenoid, it was climbing, kind of stayed plateaued, and then it climbed up pretty high, 60% duty cycle. When it climbed up pretty high, you could see what it did to my slip speed. I'm only at 5 RPM right now. And you really don't see it on these 4L60s, especially these older ones. You won't see it at 0 so much, because 0, remember they're calculating output shaft speed and engine speed. So there's a lot of stuff going on in between those two inputs there. And it's just not going to be as fine-tuned, or the measurements aren't going to be as accurate. But 5 RPM would never set a code in this transmission. It's got to be like, if you couldn't maintain 50 RPM or less for a period of time, I don't remember how long it is, but it's pretty high, it's like 20 seconds. If you can't maintain at 50 RPM or less within 20 seconds, or for 20 seconds, it will then finally set a code. So 5 RPM, 10 RPM, 20 RPM, it's actually not that big of a deal. They'll pulse width modulate the solenoid up, and they'll rarely go, as you can see here, higher than 60%. Because once they see it probably in the single digits, they figure they're there. And the torque converter clutch is, for all practical purposes, it's being controlled. Here, these slides are going to talk about the 3-2 downshift. Now, on the newer 4L60Es, they actually were able to get rid of the 3-2 downshift solenoid. They were able to do that because the software got a little bit better, and they were able to control the pressures during the downshift, so that way you wouldn't get a bind or a flare. If you remember earlier, I was saying that this 3-2 downshift and the 2-3 upshift are the only shifts that you have to time the apply of something and the release of something. Well, apparently they never got the downshift figured out too well, because they've got, with the upshift, all they did is apply fluid pressure. They had the 3-4 accumulator accumulate it. They forced all the fluid through this 3-4, or this, where's it at? This orifice number 28 right there. And then they dealt with the accumulator that occurred right here in the servo. So that fluid pressure that would go in, so they didn't have that many issues with the upshift, because they didn't really have to do too much other than a normal accumulator and an orifice. And so they didn't really have that big of an issue. But when you're downshifting, really there's a couple states of downshift. If I'm just coasting to a downshift, like the traffic light turned red, and I got my foot off and I'm just coasting down to a downshift, I'm going to downshift 4, 3, 2, and 1. That 3-2 downshift when I'm coasting is going to be completely different than when I'm cruising at 45 miles an hour on a road, a 2-lane road, and I have to pass somebody, and I stomp on the throttle and it downshifts from 3rd to 2nd, because now I'm doing this under load and I'm forcing the engine speed up, as opposed to coasting downshift where I'm just letting it drop down into gears and I'm not really intending on raising the engine speed up and delivering torque. So I don't know which one necessarily was the one they had to work out the most, but they have to operate this 3-2 control solenoid, and by operating the 3-2 control solenoid, they either force the fluid when it releases, it has to go through both of these orifices, or it can bypass orifice number 12 and just get forced through orifice 13. So really the whole purpose of this solenoid and this valve is to determine whether fluid has to flow through 12 or it can go around it. And you can see, I mean, it's probably a big thing. If they can eliminate that, it can save a lot of money in the long run. There's just a lot of these transmissions are being produced. That would be one less valve, one less bore, one less spring, one less solenoid, one less circuit, wire, less driver in the PCM. There's a lot they can save. That would be a enormous savings, and they did. It took them a long time, but they eventually figured out a way to get rid of that. The purpose of that 3-2 control solenoid is to determine the rate of clutch release when we actually downshift. The fluid that's leaving this third accumulator, it's either going to be forced through 12 and 13, or it can bypass 12 by going around. Our more modern transmissions, our latest model 406Ds don't even have this 3-2 control solenoid, as I just mentioned before. But from 96 to whenever they get rid of it, which is in the mid 2000s, let's say 2005, they had a on-off type solenoid, just like a shift solenoid. So basically, it was going to operate in one of two modes. It was either going to force it around it, and you can see there's still an orifice there, orifice 14. So it's not like we got rid of the orifice, we just changed the orifice. Instead of that one, actually we can go through both. We always have this one. We can always downshift through that one and 13. But now if we open this up, if we move this valve back over to the left, we would allow fluid to also go through 14 as well. So it'd have a parallel path. The earlier ones, when they first came out with the 4L60E, 93 to 95, those 3 years, they actually had this as a pulse width modulated solenoid, so it actually created a variable opening. But apparently they got away from that. They realized they didn't need that, and they went to this on-off type where it either went through this extra passage or it didn't, and then they figured out a way to get rid of it completely. So here is the kind of the scenarios on how it works. When it's electrically off, there's no 3-2 signal pressure, so there's nothing here. The spring shuttles this valve over to the left, and the fluid can, I guess I shouldn't say bypass that orifice, because it always can go through orifice number 12, but it has an extra orifice. It can go through orifice 12 and 14, so it can get through those two orifices quicker. What that's going to do is it's going to allow this band to reapply quicker, because if I can get that third pressure out from around that servo, I can get the second servo piston to push the servo pin and apply the band a little sooner. So the solenoid turns off. We say that we do that for lower speeds, 45 miles an hour or lower, because we want that band to come on quicker. Think of a lower, like a downshift situation where you're coasting down. We're going to want that to apply quicker because my engine speed's not necessarily going to climb up higher. The flip side of that is that at higher speed downshifts, if I'm on the throttle, I actually want the band to come on a little slower, because when the 3/4 clutch releases, I want to give it time for my engine speed to rev up, and then boom, the band applies. So in a sense, if I wait for the band to come on until my engine revs up a little bit, that would be good for like forced downshifts when you're trying to pass somebody. Solenoid off results in no signal pressure, allows for a faster release since the fluid has additional route around the orifice number 12. When it's on, we have maximum pressure, and we don't allow fluid to sneak around that and go through orifice 14. So everything has to squeeze through 12, and then everything has to squeeze through 13. That slows down the reapplication of that band. And as I mentioned before, the higher the vehicle speed, the solenoid remains on. The slower the accumulator fluid release. If we allow for a slower release, that lowers the band application, and that allows time for the engine RPM to climb up for the downshift. Whereas at lower vehicle speeds, the solenoid is off, we have a faster accumulator fluid release. The fluid can get its way out quicker, and that band will come back on quicker. This screenshot here just basically shows what you can see. And this is through a Tech 2. I'll probably at some time record this with a snap-on, and the reason why is because they don't give us the ability to graph out what the solenoid's doing. the solenoid just blips on for a short period of time. But you could see here I was going about, at this point I was going, it said 56 kilometers an hour, so it's about 35. And I forced myself from third gear to second gear. So I was on the throttle when I was doing that. You can see my throttle position was at 78%, so I forced the downshift, but it was at a slower speed. So the downshift actually kept the solenoid off. They didn't need the engine speed to climb up as high. You can see my engine speed only jumped up to 2400 RPM. Now if I was going faster, if I was going 45 or 50 and I stomped on the throttle, and that required my engine speed to go up to say 4500 RPM or something, then there's a better chance that the solenoid would be turned on, and that would allow that clutch to apply at a different rate.